Excited today to talk to you about how you could, bridge the classic world of machine learning kind of pipelines with the world of LLMs. For those of you who are online and listening, I'm just going to publish a quick poll. Would be great if you could answer, just to give us a bit of a sense of who you are, and then otherwise, in terms of just a little bit while you're answering that, a little bit about us. Elijah and I, collectively have almost 25 years experience building kind of machine learning and data platform systems. I've spent most of my career in Silicon Valley, Elijah as well. Also, he's spent some time in New York. We worked together at Stitch Fix for a long time, and that's where some of the learnings that will imbue on you come from at Stitch Fix, building tools for over 100 data scientists. One of the things that we built there, and the only thing that we open source, was Hamilton, and then we decided to start a company around it. Thank you for everyone for answering the poll. Some results coming in. It's useful. I see most people are using ML. Others are just starting to do LLMs. Cool. So LLMs, roughly a year ago, no one really knew what these were, but in the last year, this kind of space has been on fire, right? It's very nascent, very hot topic, and so in which case, for those of you who know kind of classic ML, or dabbling with or going straight to LLMs, you might be trying to think, are these two things the same, or are they pretty different? And so in this talk, we hope we'll give you two things. One is a mental model to help kind of mentally how equate these two things and how they're kind of pretty similar, and then also a tool set that you can use for both, which is Hamilton, which will be the second part of the talk. So in this first part, I really just want to leave you with some sort of mental model that roughly equates machine learning pipelines with LLM ones. And by doing that, and I guess one thing to note is this is a 25-minute talk. So and we have two parts, so we aren't going to dive too deeply into things. And so in which case, apologize that if you're looking for something a little deeper. But otherwise, let's compare some pipelines to kind of see how we can equate these two kind of worlds. First, let's start with inference. Say we have an LTV, we're trying to do long-term value prediction, which is a classic ML kind of case, and say we're doing some text summarization. To do inference here from a pipeline, a lot of things you think about and you need to do, they're pretty similar. You need some inputs, and one you do feature engineering, the other one you pass things into a prompt, you then pass it to a model, and then you get some output. Looks pretty similar, right? The one thing to note, though, is there really isn't any feature engineering, so to speak, with LLMs. Instead, you kind of have this prompt that you kind of then fill in with some sort of context. In terms of what actually constitutes a model, right? This is where I think the two words are the most different. In the classic case, you have some weights and some features that represent a model. In the LLM, it's really it's like a prompt template that you fill with text along with an LLM foundational model paired together constitutes a model. And because of therefore it's a new model is just a matter of tweaking a template. And so the way that I like to think about it is a prompt template is a bit like a hyperparameter. And so together with an API, you get a model, right? And because of that, the iteration pace, it's much different. So within the LLM world, it's much easier to get to production and build something versus in the classic kind of ML case. But in terms of when things are in production, you still have the same kind of concerns. So how do you version the model? How do you know what's in production? How do you understand, what it was today versus, 6 months ago if you're like looking for changes, right? You still have the same observability and evaluation needs. So making sure that the output matches your expectations. Having the same observability on the inputs to help you debug things. And then obviously connecting the outputs with some sort of, business metric or something that you need to evaluate to ensure that actually, not that they're only doing things correctly, but then also that they're moving things in the right direction for you and your business. In terms of deployment or serving infrastructure, etc., like there's nothing really new here. People were already dealing with APIs for inference. The only real kind of difference is that if you're doing any LLM stuff or you're trying to host stuff internally, you're going to need GPUs. Whereas in the classic world, you could get away with just CPUs, but with deep learning and such, people have already been using GPUs for serving for a while. In terms of training, at a high level with LLMs, there really isn't much training because you may be doing this hyperparameter tuning where you're tweaking a prompt. But in the simplest case, there really isn't a training pipeline per se with LLMs. Whereas compared to classic ML, to create a new model, you need this kind of pipeline to fit a model. But eventually, anyone who's doing LLMs is probably going to be doing some fine tuning. This then looks pretty similar in terms of the pipeline or the structure that you would set up to train a classic model. Difference being there really isn't any feature engineering, but you do need some sort of labeled inputs and outputs to then be able to fit a model, right? Which isn't too different from the classic case. Note though, evaluation is fuzzier with LLMs, so you're dealing with text. Those who come from an NLP background, no, this isn't really anything too new. But in terms of time spent, if you're going to be doing this stuff, you're going to be spending a lot more time on evaluation and trying to get that right with LLMs than say the classic case, as it were. And then from a training perspective, you need GPUs if you're ever going to do anything with LLMs yourself, whereas in the classic case, you could get away with just CPUs. Just to compare something more complex, so a recommendation system versus, say, a retrieval augmented generation system. So example of that is, say, at Stitch Fix, where they were recommending clothes. There was a recommendation system for it. In the LLMs, you might be doing a knowledge, question answering kind of use case. Both of these, actually look pretty similar in structure. Again, nothing really too new. Both of them, you have some sort of query that then you're getting some candidate set for. And one, it's items to kind of rank and feature engineer. The other is to get features for, and then the other is taking some text, getting an embedding, and finding similar documents. You're then potentially ranking, filtering them, and then passing it to a model that then kind of spits out an output. And so the model in the classic case, re-ranks all the items potentially, but in an LLM, you're providing that as input, and then the LLM is figuring out what to use from that to then provide an output. You have the same productionization concerns that you need an engineer for, right? You have the same kind of debugging concerns, observability, evaluation. So you need the same kind of hooks and some systems in place to understand whether things are working. You need to connect this with some sort of data store, feature stores, a vector database or database. Vector databases aren't actually anything new. They've actually existed in the classic world, right? They just come to the forefront since there's a larger need for them in the LLM case. And then you're going to be backing these up with some sort of ETL or extract, transform, load process or pipeline to feed in and take items and create features. And then in the LM case, say take PDFs, embed them, and put them into a place that you can then search over them. In terms of the classic world, to get something to production classically requires a lot of engineering. There's a famous paper by Google that kind of shows the point being that your machine learning code is pretty small. But you have to engineer and write a lot of other software to kind of get this kind of machine learning stuff to production. And so invariably, there's still there's still the problem of pipeline inheritance. So most people don't like inheriting someone else's machine learning pipeline code, right? And it's because of this kind of requirement of you still have to engineer a lot. Our kind of high level take on this is what we've seen at Stitch Fix in our careers is that usually this is because people have over engineered abstractions or then essentially make it hard to test quickly that you are changing something, you're not going to impact something downstream. It's going to be hard for you to potentially swap out a component or make things kind of modular. And then in machine learning, with say feature engineering, how do you make sure that you can classically or easily kind of reuse things? This can become pretty difficult if you're dealing with kind of custom in-house abstractions that most people end up engineering. In the LLM world, unfortunately, it doesn't really simplify any of this kind of software engineering requirement, right? The things that you kind of want to add into your pipelines are going to be, similarly require just the same amount of engineering. The space is pretty nascent. As I said, it's only really been around a year, and already people have reacted to over-engineered abstractions that made it hard to quickly test and be confident in something, but then also change something. For example, classically prompts and swap things out as you need to. So, for example, vector databases. Choosing your abstraction here can really hinder what you can do, and especially if as the field has been moving pretty quickly, this is something that people have been facing. In terms of, so this is where kind of directed acyclic graphs come in. I think, hopefully I've shown you from a pipeline perspective structurally, things are pretty similar, and that they also, with LLMs and classic ML, you still need, you have a software engineering challenge. And so let's talk about now how we can kind of think about unifying more easily, more closely unified classic ML with LLMs, as well as work to solve, the software engineering challenges, as we'll kind of see, which Hamilton kind of helps you with by modeling things as directed acyclic graphs or DAGs. For those who don't know what a directed acyclic graph is or a DAG, it's effectively concept of nodes and edges, where nodes represent computation and an edge represents the flow of what happens to be computed beforehand. In general, I want to say DAGs are everywhere in the code you write. So here I have some procedural pandas code. It is in fact can be modeled as a directed acyclic graph, right? So you can see here we're creating columns and appending it to a data frame. This can this computation can be modeled as a directed acyclic graph pretty easily, and this is in fact what your kind of compiler is kind of doing under the hood anyway, or interpreter. If you're not new to the world of LLMs and you've used a library such as LangChain, it has some, makes it pretty easy to get something up and running. It is in fact, just effectively stitching together a few function calls to create a directed acyclic graph as well. Moving on to, just to kind of prove the point a bit more. So machine learning pipelines, you can draw this kind of diagram of structure of like what's supposed to happen to kind of fit in a model. Classically, you would then implement this in production in something, an orchestration system like Airflow, which in fact forces you to also model this as a directed acyclic graph. But what's happening within these steps, right, is actually, ML pipelines are in fact a DAG of DAGs, where you're at a macro level, you're scheduling, extracting some data, creating a training set, fitting a model, doing inference. In each one of these steps, you're in fact, your code is actually, can be modeled internally as this kind of micro DAG as well. And so this transfers over to the LLM pipeline world. So in the case of the RAG example, each one of these discrete kind of computational steps, again, can be broken down into, some sort of series of micro DAGs. And so to kind of, round out this part of the talk, hopefully I've kind of shown you that at a high level, the LLM pipelines are pretty broadly equivalent to classic ML ones. You have the same shared software engineering challenges and productionization concerns to a large extent. But the point to take home with LLMs is that applications can be developed much faster, and in fact, your pipelines will have to need to be adjusted to be able to change more quickly as the field is kind of progressing. I briefly blew through the DAG section, but at its core, classic ML and LLMs workflows or pipelines can be modeled as directed acyclic graphs. And so my hot take here is that a DAG is all you need. Right. And so in terms of abstraction, if you're writing code and you can't represent it and it's not easily represented as a DAG, then the rest of that is an over-engineered abstraction. Over to you, Elijah.
Thank you. You just need that. Cool. I'm just going to share my screen, the riskiest part of any talk, but I think I got it. All right. Thanks, Stefan. So in part one, we talked about the mental model and justified why DAGs, our favorite word, are a really good abstraction for this. In this part, we're going to talk about some tooling that can help you get started with DAGs. So we're going to talk about the tool we created called Hamilton and how you can use it to represent both ML and LLM pipelines. All right, so what is Hamilton? Well, I'm going to throw at you a definition that's got a lot of words here. So Hamilton is a micro-orchestration framework for defining DAGs using declarative functions. And we're going to go over each one of these pieces in detail. But the whole goal of it is to give you a bunch of sort of software engineering best practices and make them really easy. So make it easy for you to build highly testable, self-documenting pipelines that are very modular and encourage reuse. It's all open source. You can install it in PyPy. The package is called SF Hamilton because it came from Stitch Fix where it used to work. And you can try it out online at tryhamilton.dev and run in the browser so you don't need to install anything. There's a link to this in the chat too. Cool. So as Stefan went over, micro-orchestration versus macro-orchestration. Macro-orchestration handles this whole thing. You might know tools such as Airflow, Metaflow, they're going to be speaking right after us, that think sort of a macro-orchestration level. Micro-orchestration handles what happens inside these steps. So the actual logic, how the data flows, how it's transformed, and where it's saved, that's all the micro-orchestration piece. Again, we showed this, but to hammer home, Hamilton DAGs replace procedural codes. We have these operations on a data frame. You might be very familiar with this in a feature engineering context. You're making sort of these monolithic changes. This can actually be represented as a directed acyclic graph. You can see to calculate spend mean, all you need to know is spend, and to calculate spend zero mean, all you need to know is spend mean and spend. You don't need to know the other ones. So you have an implicit ordering with a natural set of dependencies that represents this computation. Cool. So in Hamilton, we deal with declarative functions, and functions declare A, what they create in the DAG, and B, what dependencies are required for computation. So you can, but you don't have to run these functions directly. And in Hamilton, you don't actually. And when you read the function, the idea is you should be able to understand everything about it, what it does and what it needs and how it works. So this is a notion we call internally, they're called named pieces of business logic. The idea is every component of your DAG should be nice and self-contained and really give you a sense of exactly what's happening. So, talked about what it is. It actually came from a very specific problem that you've probably all seen before, which is that of debugging a data frame. Data frames are often created using a series of complex code and transformations. And we were having a lot of trouble figuring out exactly what happened, why one column was wrong. So we wanted to sort of rethink the world and come up with a way to compute this data frame. The idea was simple. What if every column, or every output column in this case, corresponded to exactly one Python function? And what if you could determine the dependencies from the way that that function was written? So a one-to-one mapping of function to column. That's how we came up with Hamilton. In Hamilton, the output, sort of the column in this case, but it actually works for more than just data frames and series, is determined by the name of the function, and its dependencies are determined by the input parameter. So to turn it into a node, you take the function name, that's the node, and the dependencies form the edges. Therein is a DAG. This isn't actually new to Hamilton. If you've seen PyTest fixtures, I think they came before. It uses the exact same sort of terminology. There's sort of a structure, and Dagster software-defined assets came afterwards, which uses a similar concept. So how does this compare to the procedural code we showed you before? Well, instead of writing it line by line, where you're managing a monolithic data frame, you declare each step as a function that handles a specific set of data, right? So in this case, instead of doing dfc equals dfa plus dfb, dfd equals some transform, you define c and d. C depends on A and B, and D depends on C. And this is sort of the entire set of code you need to write. All right. So what does the full hello world look like? Well, we've defined our functions in the step before, and we have something called a driver that tells you what and when to execute. So we handle the module. So first you import your module that we defined above. Then you instantiate your driver, pass it some data and the module. Next, you actually execute it. You say which nodes you want. And Hamilton's smart enough to just execute the ones you want upstream. And finally, you've got the result. So this is the full hello world. You can copy this code and run it in Hamilton, and it should be pretty easy. There's a lot more to the framework as well. We won't go sort of in depth into this, but we have a bunch of decorators that sort of form higher level operations on top of functions. So you can attach metadata to your functions. You can repeat them with different parameters. You can do data validation. The only one that will be useful for the rest of this talk is called config.when. And the idea is you can sort of do conditional transforms. So have one function included in the DAG in one case and one included in the DAG in another case, and be able to swap between them. Remember, Hamilton is also sort of a new way of writing Python functions, but it isn't opinionated about the tools you use to scale, and has all sorts of natural integrations with a bunch of them. So you can use any sort of Python object, run Hamilton in any Python context. And we've seen things from running Hamilton on Spark, Ray, Dask, Fast API, Flask, Jupyter Notebook. The world is your oyster here. Cool. So let's go over some examples. I'm going to talk about how we can use Hamilton for sort of more classic ML, then for an LLM pipeline, then for a combination of both. All right. So let's dive into feature engineering here. The high level is, or let's dive into machine learning and focus a bit on feature engineering, sort of feature engineering plus. The high level is that we're going to define one function per feature. So they're nice and self-contained. You have sort of modular unit testable components. Join them together and run them as part of the Hamilton driver. Utilize this config.when decorator I talked about to swap between online and offline implementations, and expand out to more components of the machine learning lifecycle. Okay, so here are some features. You've probably seen code that looks like this because it's just operations on a pandas series, but now we've got them broken out into nice, clean functions you can use in a lot of different places. In this case, these form a DAG together, and as part of a bigger DAG, create our sort of whole feature engineering pipeline, which might be one of those steps in the macro orchestration framework. But now we've got it nicely put together. We can figure out exactly what's happening, and we can understand lineage from a very fine-grained perspective. Note that if we have some features that might be different between batch and online, say you're querying a service online and you're loading a table in batch, we can use config.when to switch between the two modes. In this case, we get our survey result data from different cases offline, from different locations offline and online. And we have client login data that we get from a service online and load up a table in batch. Right. So you can use this to keep most of the feature engineering pipelines the same for the map functions that we saw before, for the sort of the simple series to series functions. And for the more complicated ones, you can switch them out. Then it gets pretty easy to add pieces on top of this. So you can add in machine learning inference and training as needed. In this case, I'm kind of making a joke here and just instantiating a model for training it. But you would imagine that due to sort of the modularity and ease of putting new pieces in the DAG, you can train your model and then do predictions right after that. Cool. Let's talk about how this works for LLM pipelines. Well, if you're familiar with sort of common LLM terminology, you'll notice that there's sort of an idea called chains, which is sort of little components that you can call together. We're calling those capabilities, but the idea is you define these capabilities or chains as DAGs, and nodes, the functions, can form prompts, API calls, external data queries, data transformation, really whatever. It's all just sort of written in Python, and you can sort of bring your own abstractions or bring your own tools. And then you can sort of tie them together with a control flow that you create, or sort of an agent. They can take the result and feed it to the next execution, so manage state, or maybe even use an LLM to decide which DAG and how to run the next one, and sort of go from there, building out more complex stateful systems. You can swap out between foundational models, vector stores, etc., all with config.when. So what does this look like? Here's a pretty simple DAG to capture an image. And I know this is a lot of code, but I'm hoping it's pretty easy to understand as to what's happening here. We're creating a prompt and then passing it to OpenAI, right? You've probably all sort of seen code that looks something like this. And we've got another one for generating an image, right? Take a prompt, generate the image from the prompt, and save the image out. Pretty simple. Cool. So we've got these, and these start to form a toolbox, right, of different little DAGs that can be used for different LLM capabilities. So you can select which DAG to execute based on the context, where you are in the application or what's happened previously. Run in the process and do something with outputs. Display them to the user, store a state and context, and feed back to the next execution. Even write back to storage for fine-tuning later. Really, you can do whatever you want. It's just these sort of like building blocks. You can even do what I did and embrace some chaos. Feed a caption from ChatGPT to an image generator in DALL-E with a while loop and 2 lines of Hamilton code. Blog post coming soon about this, and end up with something really cool. I was just having fun with this yesterday. So, all right. So now let's take a brief look at how you might even combine LLMs and ML together. And many problems you hit will require both. For instance, say we want to customize embeddings. We want to pass pairs of similar and dissimilar text that we consider for sort of our space. Query a foundational model for the embeddings, train a model on those pairs, and then project your embeddings onto that space. Right? This actually comes from the OpenAI cookbook. You download all this code online. We have in the new thing called the Hamilton Hub that we'll share shortly. And the idea here, you don't have to really get too into depth into this because I just put a big, pretty DAG to show some eye candy. But in this case, we're doing both sort of querying a foundational model and training a model using classic ML. You can swap in and out pieces, use ML for one piece, use LLM for other pieces. It's all nice and modular and broken into components. The idea is to use them for both LLM and MLs, allows you to bring your own tooling, choose which piece you want for which specific job, swap out the components, implementations, etc., visualize, test, and reuse all those different components as I showed before, and do all of this with one tool where you can delegate to whatever other tools you might need. So you're avoiding the sort of over-engineered abstraction. All right. So in summary about Hamilton, we wanted to argue, or we're arguing that modeling your DAG as self-descriptive functions allows you, sort of affords you a lot, right? You can use the same tooling for LLM, ML, and data processing, so you're not reinventing the wheel every time you switch between them. You can rerun in multiple contexts to save code and headaches, reuse DAGs to build really cool things, and build all of the above as modular, testable, self-documenting software. The goal is to never fear inheriting somebody else's code. All right. So taking a look back on everything we talked about, the mental model section, LLM pipelines are broadly equivalent to classic MLs. That's what we were arguing. But the LLM field is moving, changing quickly. While traditional machine learning isn't going away, you're going to need pipelines that you can easily swap out pieces and manage and build quickly. You can model ML pipelines as DAGs as well as LLM pipelines, and we would argue that it is in fact both sufficient and necessary to build a really sort of like strong, well-modeled system. Hamilton can be your unifying tool set for this. Software engineering best practices for free and can do both large language models and LLMs and is meant to handle change. So you can easily swap out components, develop it, and make changes and test them against each other. So next steps, you can download Hamilton on PyPy, go to tryhamilton.dev, all these links are in the chat. Go to the hub.divers.io to get started with something quickly. Star the repository on GitHub. We appreciate it, lets us know that people are interested. And join Slack if you have any questions. We also are going to be around later to answer questions and are in the chat. So thank you so much. I really appreciate your time, and we would love to hear any questions. Feel free to reach out to us.
Stefan and Elijah, thanks so much for that great talk. So we'll just give it a sec here to see if there's any questions that show up. That was a lot of information you covered there. So.
Yeah, we were slightly ambitious with what we wanted to cover, but
you did it. It's great. Oh, there's something that's coming in Q&A. Did I see that? Or, yeah, could you transform a Hamilton DAG into something, for example, an Airflow DAG?
Yes.
Yeah.
There are multiple. Yeah, I'll take this. There are multiple ways. This is actually something we've been working on a lot recently. There are multiple ways you could do it. The easiest way is to sort of take a subset of the DAG, load data from one place and write it to another place. And then you have an abstraction where you don't actually have to think about Airflow. The next thing we're thinking about is, and so you can write you can call out the Hamilton inside Airflow and that's effectively transforming it. The next thing we're thinking about is building actual compilers that could take a Hamilton DAG and compile it to Airflow. And then you could say compile it to Metaflow or Dagster later on.
Yeah, we have a blog actually on how you can use Hamilton with Metaflow. So this is what the first step of how you can combine the two. But yeah, it's on the kind of the roadmap of how can we allow you to group a set of nodes into one computational task and then help generate the Airflow code that will then run the Hamilton code for it. Good question. Thanks, Simon.
Excellent. Well, if there's no more questions at this time, there's something that came in. Do you see that in chat? If you want to take a quick.
Yeah. So I think if I understand correctly, the conversation is the question is Hamilton brings added value to the LLM and how does it work, but largely to the chain of operations. That's what we're focusing on now. So one thing we found is that we like to talk about over-engineered abstractions. Agents sound really cool, but I think the biggest thing that people need right now is sort of well-structured code that is resilient towards failure, and Hamilton can help give you that. And then we have sort of more things we're working on in the sort of agent space that I alluded to that we're going to be developing soon.
Yeah. So awesome. The Hamilton helps structure, the capability or the thing you want an agent to do. We've also found that most people, for most of the purposes, when they want to go to production, end up really heavily customizing an agent as well. And so in which case, there really hasn't been an abstraction that fits well for them other than, a Hello World demo. But, if you have, use cases or feedback, we'd love to learn from you and see how, we could, build something on top of Hamilton, for example, that is more agent-based that then, fulfills that kind of requirement.
Great. Thank you. So with that, thank you, everybody, for coming to the session. Thank you, Elijah and Stefan, for that great presentation. And to everyone here, enjoy the rest of PyData Global. Take care, and we'll end the session there. Thank you.
Thanks everyone.
So much.